Hey there! So we try to write our kernel from scratch, and to do that, in order to be efficient, I sometimes leave some features that are not interesting to do later. And lately I had some time and I decided to work on some of those things that we've left off. So going through this list here, first I started looking at heap allocation, and then this led me to go to our allocators here, especially our body allocator. So if I go to body, here we had a few to-dos here, but the most important thing we didn't actually note here is to handle alignment constraints. There we go, if I can't type. So I actually went on to do this, which was not without challenges, but yeah. So here, this was what we had before. We just absolutely ignored anything that had to do with constraints. So to test for that, what I did is I found this. So I wanted to have something that auto-checked for alignments. So I went on to implement something very similar to this, but then I found this in the standard library. So I just used it. This is a validation allocator. It's somewhere within stud.mem, I think. So what it does is fairly simple. It takes an underlying allocator of some type, and then it just hooks its vtable to these functions here. And what these functions do is just they allocate from the underlying allocator, and they do an alignment check on the result. And if the alignment check does not pass, then you get an error, and you have to look at why your allocator is not allocating the alignments correctly. Right, so I did that and I had the error, so I went on and checked that now we do allocate correctly. So changes I've made to the allocation. So let's go to allocate. Where is allocate? There we go. So here, so now we have the alignment. We take the alignment and we do something here with it. We basically align forward the size that we want to the alignment that we want, so that we find the bucket that best suits that alignment that we were asked for, and then we use that to allocate. That was fairly easy to do. So I went on and checked that everything was correct, but then I've also wanted to add more safety to this allocator here, and basically I wanted to check for memory leaks and for double freeze, stuff like that. So I remember that we had also this to-do items that was here, so debug info and allocation tracking. So I went on and added this safety config flag here that by default in debug and release safe modes will be on. But what this does is it adds to the body allocator this block of data somewhere here. Otherwise, it just defaults to a void. So this would take no space in our struct. But here we go on and we track the allocation size, the allocation line size. We track the allocated buckets, as well as we track the stack traces for every allocation and free operations we do on a bucket. Well, I shouldn't say every, but the last allocation and free for every bucket is tracked, basically, in this array here. We track a depth of num traces, and here this numTrace type is just basically 2, which is allocate and free. And if we had other operations like resize or remap, we could have them there. But I don't want to do that. Right, so with this here, I started to add code to basically test that we handle the we fill the safety data correctly. So if I go back to allocate, let's go to function allocate, or no, allocate. There you go. So here, just before we return the pointer, I call this function here, record allocation. And what this does is basically checks that we are in safe mode, records the data, captures the stack trace, puts it into where it should be. And if for some reason that bucket is already set, we return an error, double allocation. Not sure what this does here. Yeah, it was copied from here. Cool. And here we have a similar function, record free, that gets called from the free operation. What this does is basically does the same check, records the free, sets the node to, or rather gets the node that we want to check if it's already freed, in which case we report a double free error. Otherwise, we unset it and we capture a stack trace for that free operation so that we can do this check again. Report double free, basically as the name says, whenever it detects a double free, it will go through the captured stack traces and we will print them in this format here. So double free was detected at address something. The stack trace of the current free, the original allocation, and the original free operation that was done on this bucket. Similarly here in deinit, cool. Yeah, so in deinit, we also do a safety check for leaks. So once we think we are done with the allocator, we go ahead and go through all the buckets and check that if any of those is still in use, we report a leak. And this report leak does pretty much the same thing as report double free, except it basically just looks at allocations, because we know for every bucket that's still in use, that's still marked as allocated, we know we captured the stack trace for its allocation, and we basically print those. So this was quite the rabbit hole, but it was not interesting enough to do on video. So let me just go ahead and try to show how this works. So let's, for example, just omit this defer free here. If I go ahead, I need to cd into, no, I need to go to this, cool. And if I do say build test, there we go. So this is what it looks like. So this is reporting a double free. Oh, no, wait, did I miss? Oh, cool, very nice. Let's do this. Memory leak. Cool, very nice. Yeah, so it was for leak. Just had to read that. So a leak was detected at that address, and here we get the stack trace. So we know that it was at this line here, body 698, and this is where it leaked effectively. That's very nice. So if I take this, put this back on, it should just go ahead and do its thing. I'm just gonna get rid of those things, and as we can see, the tests are good. So here, let's free this slice again, and then, or rather, let me just defer the free and then free it again. Now we can do tests, and here we get the double free, because we tried to free it twice, basically. So here we can see that we tried to free it from the defer, which is correct. Here, this is the original allocation. You can see that it's allocated, it's pointing to the correct line, so the alloc.alloc. And here is where we originally freed it from, alloc.free, which is the line just below the defer. Is that it? 700? Yeah, correct. So this actually does work for our testing purposes, but this wasn't without its fair share of pain, because in the process of doing this, I actually found out quite a few subtle bugs that I had to correct, and that led me to actually build some fairly cool tools. So if I do print state, this is actually fairly cool. So let me run this. So if I go back to just how I use my terminal, the original size, this. So here, if you bear me for a second, here you can see that we have this bucket here that's marked with a star, that has this free item here, and all the other buckets are actually freed. Basically, they're empty. So that means that here, after we've finished with our body allocator, we did free all of the memory, because the highest order bucket that basically contains the full memory of our allocator has one single free item. If I go back to this just quickly and move this print state, probably after some allocations here, for example. So if I do this, here you can see that a few things have changed. Anything that's marked with a bound sign is basically a parent that is marked as split, right? So here we have this parent is marked as split. This left child of his is actually allocated. This right child is free. It's marked with a star. And yeah, so here we can track actually the allocation state just visually on our allocator. Just was very cool to build. Right, so let me go back to a more presentable size here. Right, so that's that. And then I've actually wanted to use the thing that we've built for basically reporting the allocation and free problems, so the leaks and double frees in our basically OS, because this now works as a native application when I run Zig build test. But I actually wanted this to also be used in our own OS. So what I had to do first of all is go through the process of building a custom panic handler, and that was actually fairly simple. So if I go to main, let's go to kernel main. So here it was as easy as doing this. You basically provide a panic function to this full panic handler here, and this full panic will take in charge formatting the panic messages and then passing them to the panic function. This panic function here I defined as, let me just zoom into this, as this. We basically get a message and an optional trace address and then we try to walk the stack from there to basically go through this number of stack traces defined in our constants. And of course, this only we only do this if we have safety on. So I also define this safety constant or safety parameter in our constants so that we can add some more safety measures to our operating system. So this calls set debug capture stack trace, which basically just walks the the stack frames, looking for return addresses, and builds the stack trace for us. Puts it into this addresses array here that we pass it as instruction addresses. Once we have that, we actually can go ahead and format a custom message here with the error message that we were passed and some other formatting for our stack trace. And actually, to show this, I am going to need to go to make kernel, make file, sure, and probably just remove the release safe from here. And if I go back, so let's zoom out here to a make-b all. Hopefully this builds. Yes, okay. Here we can just get QEMU. Sure. So here's the problem. The problem is that we, if instead of printing the address of the stack trace, we try to print the stack trace itself, we will get an error message. And let me show you that. So let me just do something like get the formatter for stack trace. Sure. So if I try to build this, here is the error. So for some reason, it thinks that we are a POSIX system, tries to call into set POSIX, and that fails. So that basically just for this here, just for formatting the stack trace. And what this formatting entails is, so I tried to go into this and try to see what the formatting of stack traces entails. And basically what it does is it looks into the debug information on our binary, and it tries to load the binary from disk if it doesn't have that debug information on hand. The problem is we are running a kernel. We still don't have any disk drivers, and even if we did, the Zig standard library would not know how to interact with them. So I took it upon myself to actually build this system here. So I created this file here. Started with just these notes here. I want the bootloader, when it basically loads our kernel binary file, or rather when it loads our kernel from the binary file, I wanted to also look for debug information from that ELF file. Try to load those, give us a memory mapping of those files, so copy them into memory somewhere, and then tell us in the boot info that we have a debug section or debug info section that we can look at. This module here will read that section back and try to get basically given an address, try to find what is the symbol, so be it a function or a variable or a module or something, what is the symbol closest to that address, and also give us info about the file name, the line that we had that that error on, or we had that address on, and a few other things that can be used to basically compile a stack trace that's human readable and actionable by us if we see a problem. So I went on then to go to bootloader UEFI. So by the way, this means that for sometimes, maybe indefinitely, the BIOS bootloader is deprecated because it does not have this feature here. So I went on here into bootloader, added this boot info pointer. I added some code to check that by adding this boot info pointer, we don't move the boot info size. That means that we'd still retain compatibility with the boot info on kernel size. So because this is our main interface between our main data passing interface between the bootloader and the kernel. So went on there, added those things, and then went on to debug.zig on the bootloader UEFI bootloader size. Created this section here that basically has a physical address, a length. These determine a slice where we have copied the data for one of these debug sections. And these debug sections are basically the name of debug sections in the dwarf type or dwarf format. So these are defined by the dwarf spec, and we copy them to this, or to a slice defined by these two parameters, so an address and a length. And the address is whatever virtual address that was put onto that section header. We'll get into that in a minute. But we just have that in case we have moved stuff in our memory, or we did a memory mapping or something like that, and we needed to find our symbols again. So then I created this enum field backstruct, which basically just goes through the fields of an enumeration given here by E, and creates for every enum entry, so every enum basically literal here, it will create a field of type data. So all of the fields have the same type, and every field would have a default value of some optional of data, basically. And then it will create a struct containing all those fields. So basically what we want to see here is that this struct here, sections, is basically something like debug info of type section, and that defaults to something like this. So that's what we've seen here, and we have this times. So here we have what debug abbreviations, stuff like that. So that's what this is doing here. So fairly easy stuff. Just made sure that this is backed since we are putting this onto memory. And yeah, so right, so here we get to the important part. So here in load executable, we have loaded our kernel file. So the elf binary has been loaded. Here we get a slice, which is basically just the contents of the file of the elf. And what we try to do here is we try to extract our executable out of the elf container. So we do basically the things that we did before. And at some point here, yeah, so here we create an array that basically has the number of sections that we expect. We defined in debug section type, which are these ones again. And then we go ahead and try to, so here we've matched, this is the code we had before where we matched semtab and stirtab. We add this code on top that tries to match for every field of that enum to the section name that we are currently reading from the elf file. And yeah, if we find it, then we put it in the correct slot in our array. Then we check that we have at least these 4 sections here. Otherwise, we just bail. Because if we don't have these ones, we don't have enough data to actually do any meaningful debugging. Otherwise, we go on to load those to memory. So we take a size, which is basically a size of sections, which is just the descriptor that tells us where every section starts and how long it is, plus all the bytes for every actual section or the contents from each section. We allocate those to our kernel module memory type here, and we go ahead and do the copy. So we just basically compute slices, copy the actual slice on the elf to our destination slice that we are going to pass to our kernel, and we go on and fill in the info for every single type that we have. And then we also put into kernel info the correct debug info pointer, so showing that we have actually loaded debug info. Then I think in main we do so if I go here, if we have a debug info pointer, we put that pointer into debug info so that it gets passed to the kernel. Then so this, now we are going back to our kernel side. Here, same thing, just added the debug info pointer here, added some code here for safety reasons, just to make sure that because it was fairly easy to break this and just have the kernel run with a skewed view of the boot info and load the memory maps in an incorrect way. So this was very important to add, just to ensure that we are not doing something too bad. And then we get here, and here I basically just recopied the same code again from the other side, just because I didn't feel like doing anything more than that. And here in the init function, basically we take an allocator, we check that we have a debug pointer in our boot info, otherwise we just do nothing. And if we do have it, we basically get a sections out of that. We try to read, we try to construct this section array. This is given by stud debug dwarf, I think. Yeah, so this is in the standard library. And then we go on to basically fill in all the fields that we have there. So we fill in all the sections, and we create dwarf type here. Again, this is still in the stud debug dwarf thing, and we call this try open dwarf, which basically just goes ahead and scans the sections for debug info and pre-computes a few things. Right, so here let's do a quick test of what this looks like, because for now it's not hooked yet, so we still cannot get any meaningful stack traces. But let's try to do a few things. Let's do so let's do log.info and try to print. Let's do a multi-line thingy. Symbol name, something like this. maybe file name, and probably line. Sure. Let's try to do something like this. See if this still works. And here we are going to need to do so const symbol is dwarf dot I think get symbol, and we need to give it an allocator, which we already have, and an address. So for the address, I'm just going to do something very simple. So int from pointer, and here I'm going to pass it a let's pass it init. So we're passing it the symbol of this function init here. Yeah, sure. So this here would need to be so symbol dot we have name and symbol. Oh, this needs to be tried. Yeah. So symbol dot name, that's okay. Symbol dot source location dot, yeah, sure, let me just force that. File name and symbol dot source location dot line. Sure, let's give this a try. Cool. So yeah, let me just run this again. And we should see when we initialize the debug info. There we go. So let me just get rid of this. So symbol name is init, that's correct. It's in root projects FLCNOS kernel source debug.zig, that's also correct. And line 66. So if we go there, we are actually bang on the symbol itself. So this will let us basically go ahead and go through these stack trace frames, frame pointers, and for every address here we can basically get a meaningful function name or module name with its line, file name, line, column, and all the necessary info so that we can debug our kernel inside our kernel, which is really great. So those were the big changes that I've made, but again, there were a few smaller cleanups and stuff like that that I don't really think we should talk about. But one other thing I need to mention is that since now we have a panic handler here, we actually could just move so our where is it? Our handler here, our default handler, now instead of just halting, it basically just calls unreachable, and that is what triggers this reached unreachable code that we get here. So we get a fairly nice formatted message here with a stack trace. We could actually also do, if we go to main, for example, and we just do something like panic test, and of course it will complain that this is not good. Right. So if I run this, we expect to see just the panic handler triggering with the word test. In this case, sadly, we don't get a stack trace, but I think we could build one ourselves, because we basically get called directly from this panic message here to the panic handler. So we could just follow the what I'm talking about is if I go here. So here I'm just saying that if the first stack trace is null, which is basically what happens if it's not a panic message coming from the standard library, this thing gets null, and here we don't do the stack trace capturing. what we could do instead is say that we would like to actually start from the current stack trace, or rather the current stack frame, and then walk it back. And I'm pretty sure that we are going to find where the panic message came from, since we get called almost directly, I think, to our panic handler. Well, that's pretty much it for this one. This was more of a relaxed devlog about things that were not interesting enough to go into a video, but yeah, just to keep track of the project's progress. Until next time, I'll see ya. Fucking out.